Alpha and beta. These are current gains of BJTs, bipolar junction transistors. These are actually large signal current gains. One, that is alpha, refers to CB configuration, and the second one, beta, refers to CA configuration. Current gain means, in general, ratio of output current to input current. But here, in the case of alpha and beta, it is not just the ratio. In fact, it is the ratio of change in output current to change in input current. So, these are ratios of changes in output currents and input currents, and the changes are measured or considered from cutoff. Exact name of alpha is large signal CB current gain. Exact name of beta is large signal CA current gain. Alpha and beta, they are related. Alpha has certain significance in describing the internal currents of a transistor BJT, whereas beta is useful in describing the terminal currents of the transistor as well. It is useful highly while designing bias circuits. Alpha is also connected to emitter injection efficiency and base transport factor of a transistor. As alpha and beta are connected, beta also has a connection with emitter injection efficiency and the base transport factor. Electronic devices, BJTs, DC current gains and internal currents. Series on semiconductor devices and circuits, lecture number 3.11. BJTs stand for bipolar junction transistors. In their functioning, both polarities of the current carriers, electrons and holes, play an equally important role. That's why they are bipolar. In their structure, there exist two junctions. It is a junction device, hence junction in their name. Transistor is a term coined by contracting two words, transfer, resistor. In transistor action, especially in amplifying a signal, the transistor transfers current from low resistance to high resistance. In their functioning, there exists transfer, current transfer from one resistor, low resistor, to another resistor, high resistor. Transfer resistor. These two are two terms that gives an indication regarding the functioning of transistors. Hence, they are contracted into one word, transistor, and used to denote a transistor. For these reasons, BJT is called bipolar junction transistor. In the present session, we focus on current gains. DC current gains are large signal current gains of BJTs, alpha and beta. Along with them, we also focus on terminal currents and internal currents, the interrelationships between current gains, terminal currents, and internal currents of a BJT, that is bipolar junction transistor. Now, with this small introduction, let us move further to start the course session. A few introductory remarks regarding DC current gains or large signal current gains of BJT. Notice alpha and beta. These are current gains, large signal current gains. They are highly useful, especially beta, which is used in the design of biasing circuits for BJTs. Hence, without knowing about these two, it is difficult to have a command over the BJT circuits. Certain important points regarding alpha and beta are given here. The two current gains, alpha and beta, these are defined with respect to a transistor biased in active region. BJTs are associated with three regions of functioning: saturation, active, cutoff. Here it is said that alpha and beta, they are specific to active region BJT. Alpha is current gain in CB configuration, whereas beta is gain in CE configuration. Alpha pertains to CB, beta pertains to CE. These are actually ratios of changes in currents, changes measured from cutoff. So ratios of changes in currents. These are not simply the ratios of currents, these are ratios of changes in currents. The changes of currents are measured from cutoff, which is defined by IE, emitter current 0 with the reverse biased collector junction. Alpha and beta of a transistor, these two are related. They are not independent of each other. The relation between them is given here. Beta is alpha by 1 minus alpha and alpha is beta by 1 plus beta. Now we go a little bit deep into alpha. Actual name of alpha is large signal current gain of CB transistor. As it is too long for use comfortably, usually it is called simply by alpha. What is it? Definition is, it is the ratio of negative of collector current increment from cutoff to emitter current change from cutoff. Gain means output by input. Current gain means output current by input current. If simply DC currents are considered in the measurement, then the resultant gain is called DC gain or static gain. But here it is not static gain, it is large signal current gain of CB transistor alpha. It is collector current increment from cutoff to emitter current change from cutoff. Alpha therefore by definition is equal to minus IC naught by IE minus 0. IC is collector current DC current. IC naught means collector junction reverse saturation current. IE stands for emitter current. 0 means 0. So 1 or 2 points regarding IC naught. BJT is associated with the two junctions, emitter junction, collector junction. Emitter junction exists between emitter and base. Collector junction exists between collector and base. Emitter is heavily doped, whereas collector is moderately doped. Therefore, the reverse saturation current pertaining to emitter, it cannot be same as reverse saturation current pertaining to collector junction. Hence, I E naught, emitter junction reverse saturation, it can never be equal to collector junction reverse saturation current. This aspect one has to be kept in mind. So IC naught refers to collector junction reverse saturation current. A few points regarding alpha. It is always positive as IC and IE are of opposite sign. Its range is from 0.90 to 0.995. This is practical transistor. It can never be 1 or more than 1, always less than 1. For a good transistor, it is near to 1 but less than 1. It is a function of emitter current, PCB, collector base junction voltage and temperature. A few points regarding beta. What is the exact name of beta? Large signal current gain of CA transistor. As the name is too long to be used comfortably, usually it is called beta. By definition, it is the ratio of the collector current increment from cutoff. Cutoff means IC equal to ICBO. What is ICBO? It is explained in the next slide. So the base current change from cutoff, IB equal to ICBO. These are cutoff conditions, cutoff currents. So collector current has to be measured from cutoff, base current has to be measured from cutoff, and their ratios are to be considered to get beta. So beta is by definition IC minus ICBO, ICB naught by IB minus ICB. Some important points regarding beta. It is always positive and its typical range is 20 to 150. Small changes in alpha get reflected as large changes in beta. A 0.5% change in alpha causes a change of 34% in beta. As already mentioned, alpha and beta, they are related to each other. They are not independent of each other. A significant point, an important point pertaining their relation is given here. Small change in alpha appears as big change in beta. Now we know already what is IC naught, what is IE naught. IC naught is collector junction reverse saturation current, IE naught is emitter junction reverse saturation current. Now a few points of explanation regarding ICE naught. I stands for current, naught stands for reverse saturation current. CE means collector to emitter. It flows collector to emitter. Of course, base remains open circuited. Here is shown PNP transistor. Collector junction is reverse biased. The reverse bias voltage is connected between emitter and collector. With this voltage, with this type of bias, one can see emitter junction is under forward bias, but collector junction is under reverse bias. Certain amount of current flows, that is ICE naught. In this case, IC equal to minus ICE naught, IE equal to ICE naught, IB is IC, IE, IB. These are terminal currents with directions shown in this diagram. Standard convention is terminal currents are always entering into the transistor. For them, current is positive only when current enters into the transistor. A few points regarding IC naught. I stands for current, not or 0 stands for reverse saturation current. CB means collector to base. Earlier we considered ICE naught. Now it is ICB naught. It is illustrated here. Again PNP transistor. It is reverse biased by certain voltage. So current flows from base to collector. Conventional current. Here emitter terminal is open. Earlier base terminal is open. Now from this diagram one can see ICBO or ICB naught is defined with the emitter current is 0. Then IC becomes equal to minus ICB naught. IB becomes equal to ICB naught. It can be shown ICE naught is equal to ICB naught by 1 minus alpha with base open circuit. So ICE naught, ICB naught, these two are related. Just like alpha and beta are related, there exists a relation between these two also. Both the definitions, descriptions of ICE naught, ICB naught, they are given with respect to PNP transistor. For NPN transistors also, the definitions follow, description follows on similar lines. Now, input output current relations in CB and CE transistor. IC collector current, terminal current, it is output current. IE is input current of CB. IB is input current of CE. CB means common base. CE means common emitter. In both the cases, collector is the output terminal. In case of CB, emitter is input terminal. In case of CE, base is input terminal. With this understanding, we consider two important relations. IC collector current is always equal to IC naught minus alpha IE. Collector current consists of primarily two components. This is BJT, this is collector. One component is emitter current that reaches collector. This emitter current, while traveling towards collector, drops certain amount at the base, remaining reaches collector. This is alpha IE. There exists another component also. This component is reverse saturation current, collector junction reverse saturation, that exists across collector junction. These two together constitute collector current. So IC is equal to IC naught minus alpha IE. With a little bit of manipulation, this relation, one can obtain widely used DC current, terminal current relation of BJT. IC equal to beta plus 1, IC naught plus beta IB. This is the one that is widely. The currents here are in a transistor biased in active region. These relations hold good only when transistor is in active region. If it is in cutoff, if it is in saturation, no. The currents obey the following relation always. IE plus IB plus IC equal to 0. This is IE, this is IB, this is IC. Kirchhoff's current law says that algebraic sum of all the currents entering into a node is 0. So when you apply, we will be getting. So these two are quite important relations, frequently used relations in solving problems in BJTs. Now, to understand the functioning of transistor, we spend some time on internal currents of BJT. We consider PNP transistor. We assume it is in CB configuration. We also, from the bias voltages, we can also see that it is in active region of operation. Now, IE is emitter current, IB is base current, IC is collector current. These are terminal currents outside the transistor. This IE has two components inside. One is hole current IPE, another is electron current INE. INE is considered as a waste component. Why waste component? Transistor is one which is meant for providing a gain. Gain means roughly say it is IC by IE. For gain to be more, IE should be as less as possible. IC should be as large as possible. So somehow IE should be small. It has two components. Out of the two components, IPE, if we make IPE small, as a part of IPE is reaching collector, IC also comes down. So it is not wise to touch IPE. Only alternative, next alternative is to have more gain, reduction in INE. Preferably, it should not be there, but it is not possible to make it zero. But however, one can reduce it to small value. So INA as INA, it is not contributing anything to collector current. It is a waste component. Not only that, it is causing increase in IE. Its presence is causing an increase in IE. So there are two reasons for calling INA a waste component. One reason is it is not at all contributing anything for IC. Second thing, it is in addition causing increase in IA, therefore it is waste component. INA has to be as less as possible. It can be made less only when base is lightly doped. That is why base is lightest doped region. Okay, now IP. This current which is due to flow of holes. INA is due to flow of electrons. IP is due to moment of holes. This current travels, enters into base region. As base is lightly doped and it is very thin region, this current is able to pass very quickly cross base region and reach collect region. Traveling in the collect region, it gets collected by the collector terminal. It becomes part of collector current. The collector current, in addition to current that has come from emitter, has another component also. It is reverse saturation current. Together, IPC1 plus IC1 together is IC. A few points regarding current component inside the transistor. Point 1. The component INA is a waste as in it increases emitter current without contributing to the collector current IC at all, and hence it would prudent to make this component much less than other component IPE. IPE should be large. INA should be as small as possible. One way to make IPE large is dope the emitter region heavily. To make INA small is dope base region as lightly as possible. Point 2. The collected current IPC1 by the collector is much larger than collector reverse saturation current IC0. It is so large that IC is IPC1. Point 3. The base current has three components. Injection component to emitter INE, recombination component IPE minus IPC1, collector reverse saturation current IC0. First two are waste components, whereas third one is useful. Even though this is small, it is useful. Earlier we did a description for a PNP transistor. Now NPN transistor is considered for describing internal currents. Emitter current, base current, collector current, these are terminal currents. Transistor is a semiconductor device. So here is a junction, emitter junction. Across junction there exists two types of currents, majority carrier current, minority carrier current. If you consider emitter region, majority carrier current INA. IP is minority carrier current. As already explained, IPE is a waste component. INE, majority carrier current, this one component is very large. It travels, flows like this, like this, like this. A part gets dropped in the base region, a small part, recombination. Remaining reaches collector. It is called INC1. IC is most of it is contributed by INC1. IC naught is reverse saturation. Now, a few terms pertaining to internal functioning, internal currents, internal physics of BJTs we consider here for discussion. First one is emitter injection efficiency, gamma. Symbol is gamma. It is defined as the ratio of actual injected current into base to total emitter junction current. Gamma by definition is INE by INE plus IP. This is total current. This is total emitter current. INA for NPN transistor should be large. IP is waste component. So gamma should be large for a good transistor. However, it can never be equal to 1 or more than 1. For PNP transistor, it is IPE by IE. Another parameter is base transport factor B. It is defined as fraction of carriers that did not recombine while traversing the neutral base. It is equal to INC1 by INE for NPN transistor, IPC1 by IPE for PNP transistor. Now, here we consider the connecting relation between large signal current gains of transistors alpha and beta with internal currents and other parameters like emitter injection efficiency and base transport factor. Alpha has already been defined, but that definition is in terms of terminal currents. Here, another definition. This definition is in terms of internal currents of transistor. Alpha can be defined as fraction of total emitter current, which is due to holes in case of PNP and electrons in case of NPN transistor, which have traveled from emitter across the base to collector. Mathematically, alpha is IPC1 by IE for a PNP and INC1 by IE for NPN transistor. Emitter injection efficiency gamma and base transport factor B are related to alpha. How alpha equal to gamma B. Before closing the session, a few points regarding transistor junction voltages at room temperature. For silicon and germanium are given here. VCE sat means collector emitter, between collector and emitter when the transistor is in saturation. VBE sat, base to emitter, voltage under saturation. VBE active, base to emitter, voltage under active region of operation. When cut in, VBE cut in, VBE cut off. For silicon, 0.2, 0.8, 0.7, 0.50. For germanium, 0.1, 0.3, 0.2, 0.1. These are typical values. These are to be kept in mind. With this, we come to an end to the session. Before closing down, let us recollect important aspects that are touched upon in the present session. Definitions of alpha and beta, they are given, and their significance, their meaning, all are explained. Internal currents of a transistor, BJT, they are described, and their relation with alpha is also given. Hope this session is useful to you. We meet again in another session very soon with a new topic.